Hello, welcome to our Beyond 334 video. I want to start out by reflecting on what you've accomplished this term. I've expected a lot of you. I've expected that you learn a new programming language for many of you, C++, kind of as we went along. I've expected you to tackle big, complicated, challenging programming projects, all the while keeping up with in-depth material on databases. And you have risen to this challenge. One thing that I hope you take away from this course is that you can do these very difficult things. You are capable of you are at the point in your computer science education where you are capable of meeting these kind of challenges. So I also wanted to use this video to do a brief overview of some of the big ideas in database systems that we didn't get a chance to get to in the time that we had. So the first one is going to be distributed databases. So in the kind of systems, in the sort of algorithms that we've thought about up till now, we've imagined there is a database system on one computer accessing the memory of that computer and the disk of that computer. We've imagined that that computer might have multiple processors, might be able to do a lot of work in parallel, but nonetheless within a single computer. And that's just not the way that databases are used in many contexts in modern computing. And in fact, we very frequently encounter databases whose data and processing are spread not only across different computers, but across geographic space all around the world. Google, Facebook, Netflix, Twitter, any service that is accessible and serves very large numbers of users all around the world, it is going to have to, if all the data is in a single database on a single computer, one that there's just too much data for that, but also any one spot in the world is going to make it slow to access that from those places that are far away from where that machine is located. So not only do we want to split up work across multiple computers, or nodes as they are called for distributed databases, we also want to be able to kind of replicate our data in multiple data centers in multiple places across the globe to kind of provide fast access over the internet from many different places. So to kind of do a quick overview of key ideas in distributed systems, one question we'll ask is what is shared between the nodes that our database is distributed across. So in the kind of the picture that we've had so far, it's just we have a single machine where the CPU, memory, and disk all live together. This is what we might call the share everything model, where all parts of the system are shared and we just have a single node. We also might have a shared memory model. And here is where the picture is going to go into our sort of distributed context, where we have our multiple CPUs, and then those communicate via the network to some shared memory and disk. And so each of our separate nodes, these are our separate CPUs here, these would send communication to access memory and a kind of a shared memory and disk over the network. This is a pretty uncommon structure. There's just kind of too much overhead in this network communication to access memory in that way. And it's also the case that every node sort of needs to know what every other node is doing because all these other nodes, they're sharing the same memory and we don't want them interfering with each other. So shared memory, pretty rare. Far more common is a shared disk model, where here we have our separate nodes with their own CPUs, and they all have their own memory, and then it's just the disk that we are accessing via some network in a shared fashion. So there's kind of one singular storage, and each node is sort of retrieving and writing data to and from that. Finally, we have the share nothing model, where each of our nodes is going to be kind of hardware-wise totally self-contained, all have its own CPU, memory, and disk. And then there's still communication among these nodes over the network to coordinate kind of what work the nodes are doing, to notify other nodes that updates have been made, these sort of things. But this shared nothing model kind of has each node has complete control and fastest access to its memory and disk. And so these kind of shared disk or shared nothing models will depend on kind of the sort of context, what sort of workload we're trying to support, and kind of how much coordination overhead we can afford. And this might also depend on the details of this network piece here. Are these separate nodes all kind of in a particular data center so their communication is really fast and reliable? Or are they spread out across a large amount of space, thus kind of using the public internet for communication, which compared to being within the same building is slow and unreliable. And so this is a major design decision when it comes to distributed systems. Another design decision is kind of what can the nodes do? So there are kind of two ways to approach this. We can have homogeneous nodes. I mean, all the nodes in our system are the same. They can all perform the same tasks. And so when we have some work that needs to be done, we can send it out to any of the nodes. If one of them fails, we can send that task to a different node instead. We could even send tasks to multiple nodes and just see which one comes back first. And this is kind of a good fit for our share nothing model. If kind of all our nodes kind of can do the same tasks, have the same sort of configuration and properties and responsibilities, it's a good fit for this where they're kind of not sharing anything, so we can just sort of treat them as self-contained workers. And heterogeneous nodes is kind of the other choice, where now different nodes in our system have different roles or different tasks they can do, and it may be the case that these different types of nodes need to coordinate in order to complete an entire task. So one example of this would be a distributed system where we had some control node that queries come into, and then the control node sends this out to different aggregator nodes, And these aggregator nodes are then responsible for dividing up work among leaf nodes, with the idea being, all right, a query comes into the control node. It determines, all right, how is it going to break up this query to send kind of different parts of the work to different parts of our distributed system. It sends those parts off to these aggregator nodes, and the actual data and processing takes place at these leaf nodes. So the aggregator is responsible for, again, figuring out which leaf nodes have which data or are going to perform which part of the work, send that work down to those leaf nodes. They compute whatever it is, the sum, some query, send on the data that they have at that node, send the results back up to the aggregator, which combines them, and this all the way eventually makes its way back up to the control node, which provides the result to the user. So this would be an example of a heterogeneous design where you have different nodes kind of handling different parts of the task and coordinating between them. This would be in contrast to a distributed system where we just have a bunch of nodes that can all kind of do the same thing, have the same responsibilities. So one part of this picture is that we have these leaf nodes where I said the actual data is. And whether it's this heterogeneous picture or a homogeneous one, one of the big benefits to our distributed system is that when we have massive amounts of data, that's going to be difficult or expensive and slow, potentially, to put all on a single node. And so we want to partition it among many different nodes in our distributed system. And so we need some way to do this partitioning. So for partitioning, this is also sometimes called sharding in NoSQL systems. And there's a system called MongoDB that it's not the only system that can do this now, but when it was created about 10 years ago, one of its big advantages was auto sharding, meaning when you had a bunch of nodes in your database, if one of them got too full, as you were adding data to this database, it was ending up kind of unevenly distributed across these nodes. MongoDB would automatically move data around, rebalance it, potentially even create new nodes as a way of kind of automatically managing this partitioning for you. And this was a really powerful feature. And so our goal with partitioning we want to maximize our transactions or queries that access only one node. So if we have a transaction or a query that involves data spread across many nodes, that's going to be kind of more coordination, slower, more complicated. And so we'd like to partition the data such that to maximize the number of operations we're doing that only involve a single node, because that's going to be more efficient. So one kind of naive approach that we might take would be to say, all right, we're going to do kind of one table per partition. So like each node in our distributed system will be home to a particular table in our database. This is not ideal. An individual table could still be very big, and so it might be hard to fit an entire table in a single partition in some cases. It also makes anything that involves joins potentially going across multiple nodes, though in general joins are going to be going to be more expensive in this distributed context where our data is going to be split up. And something that's more commonly used is called horizontal partitioning. And this is the idea that we have that we're partitioning our data according to some key. So if we had some table where we have tuples that have columns, then and then we have different partitions, which I'll draw as cylinders. Cylinders, when it comes to my artistic ability. Then what horizontal partitioning says is, all right, let's pick some attribute or combination of attributes, but some key that is going to determine what which partition these go to. And so if I might say, okay, this we have different values here, and we have four partitions. So we say, okay, let's do mod 4 on this attribute to figure out what partition. Partition 0, 1, 2, and 3. So 7 goes to partition. The whole tuple here would go to partition 3. 10 goes to partition 2, 12 to 0, 3 also here, 5 to 1. And so kind of different tuples based on this key are split among our different partitions, the different nodes in our distributed system. And then for any query and you would choose this partition key such that the sort of transactions or queries that you're doing kind of involve some predicate on this key so that you would kind of go to a particular partition. So that's the idea behind horizontal partitioning. I use a sort of hash-like way of deciding which partition they are in here. I made this attribute numbers, but we could use a hash function to turn whatever it is into a number and then took it mod the number of partitions. But this part right here, where I said mod 4, has a problem because let's say my database is growing, 4 partitions isn't enough. I add another partition, partition 5, not 5, partition 4. And then I say, oh, well, I'll just change this to mod 5. But that causes a big problem because if we change this, now all our data needs to go to different partitions. 10 needs to go to 0. 12 needs to go to 2. 7 needs to go to 2. 3 can stay at 3. 5 needs to go to 0. And so you can see that most of our data had to move to a different partition just because we added a new one. And so we'd really like some approach to this that deals with this problem where if we add a new partition or subtract one goes down, that we don't have this issue where we suddenly have to move a bunch of our stuff around if we're using this hashing like approach. So there's one really cool technique that I wanted to share with you called consistent hashing. And the idea is what we were doing over here was doing mod n for n partitions. And what consistent hashing says is let's actually just put all our data and partitions on a circle. Why a circle? You'll see in a moment. But to put it on a circle, we'll do mod 360. Right, 360 degrees in a circle. We'll take a hash of our partition key, mod at 360. And so we have a circle, 0, 90, 180, 270. And the idea is that each of our partitions will have some way of assigning them a number, and then we'll take that mod 360, and so let's say that we have our different partitions here, which I'll label P0, P1, P2, and P3. And then the idea is, all right, we'll mod our data, and let's say we'll mod our data. I won't use those exact numbers because I want it to sort of end up distributed around this circle. You would multiply it by some factor and take it mod 360 to sort of make that happen. But just for the purposes of this example, we'll mod our data, and let's say our data ends up here, 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 and here. So these red X's are where our data is sort of hashing on this circle. And what we say is that the partition that a data goes to is the next one in clockwise order on our circle. So this data would go to P0, this data to P1, both of these to P2, and this one to P3. So we still have a way of assigning each of our tuples according to some key to our different partitions. But now imagine we're adding our fifth partition. We might add it, let's say we add it here. Now, if we add a new partition, the only kind of region of our kind of space in which we're hashing our data, the only region that might be affected by this new partition is the area of the circle between the new one and the previous partition as we think about clockwise order. So it's just this segment right here. These are the data points that might go into this new partition. Everything else is unaffected. So this actually would mean that this data point would now go to the new one instead of P2. And this applies also if then P2 got removed, the point that was going to P2 would just go to the next one in clockwise order, P3. And so this consistent hashing deals with this problem when I was just taking mod n for n partitions, where adding and removing partitions affects only a small amount of the data and makes that process much less painful compared to having to move a bunch of values around every time that happens. So I thought this was a really neat and an elegant kind of technique for dealing with this problem, so wanted to bring it up in this beyond 334 topic. All right, so last couple points on distributed systems. Want to talk about bring in some of the other topics that we've covered. So I guess one point to make is that a lot of the things that we've talked about, query planning, query optimization, join algorithms, sorting, aggregation, how things are actually stored on disk. These are all things that work basically the same with a distributed system as they do with a single node database. We're still using external merge sort. We're still keeping things in pages. We're still going to have buffer pools for the particular nodes. But one thing that we will think about being different is kind of what does it mean in the distributed context to have our OLTP workload or OLTP type database versus our OLAP database. So for OLTP, the major concern is transactions that are going to affect or involve multiple nodes. And in particular, I'll talk a little bit more about this in a moment, but let's say we have a transaction. It makes some sort of update, and it commits. Well, it's running on, say, one node of our database. But when the transaction commits, we want all of the database to reflect that this transaction has committed. And so there are a lot of algorithms and techniques for achieving consistency in a distributed context. Some are sort of strict, like there's an algorithm called two-phase commit, where to commit a transaction first has to tell some central control node that it wants to commit. That control node then talks to every other node, all of whom must say yes, okay, it's fine for this transaction to commit, and only then is the transaction allowed to commit. So there's kind of two phases. It has to ask, all the other nodes have to agree, and then it can commit. And so that, of course, obviously introduces some overhead into the process of committing. Other approaches are much less restrictive. So a lot of NoSQL databases provide not the ACID guarantees, which the kind of atomic, consistent, isolated, these are hard to do in a highly distributed context. And so they provide base properties. And so a little chemistry joke, acid and base. Base stands for basically available, soft state, and eventual consistency. And so this is saying that the database, basically available, we want the database to be highly available. We don't want the database to be non-responsive for some long period of time while it's figuring out if it's okay for some transactions to commit. So we're going to emphasize it's just going to be available, and we'll deal with the consequences of that in other ways. Soft state says because we're putting this emphasis on availability, we're not always waiting for stuff to be consistent. The state at a particular node that a particular operation sees may not reflect updates that have been made in some other node or other part of the database. And eventual consistency says, well, for a given set of inputs, if the database, if you wait long enough if the database is running and you wait long enough with no further operations, all the nodes will eventually be consistent with each other. So there's some protocol by which changes made at one node sort of propagate throughout the database, but there are no guarantees when that will happen, just that it will happen eventually if the database keeps running. And so, as you can see, these are 4 different use case emphasizing different goals than our ACID properties, and there are of course trade-offs involved. When NoSQL began, the sort of attitude was this ACID stuff is so slow, it's unnecessary, and that thinking has sort of shifted as time has gone on. NoSQL and kind of non-relational databases are tending to provide stronger guarantees, realizing that there is some value in being able to do that. Okay, so that's sort of the OLTP side. be a little more brief on the OLAP side, but the main concern is that an OLAP query involving lots of tuples, like a big range of data over a long period of time, or lots of analysis of a large amount of data. We really want to minimize the amount of data that has to be transferred between nodes. So in these kind of OLAP distributed databases, they're going to be focused on how can we efficiently partition or replicate the data, and how, when there are queries that involve data from transferring a bunch of different nodes, how can we kind of take that into account to make future queries like those faster. That's going to be a big focus of OLAP distributed systems. Okay, so that's what I wanted to blow through for our distributed systems. And kind of another big category of databases that didn't really talk much about this term is in-memory databases. So something that's kind of dominated our thinking in this course is the fact that our data is on disk. And that disk is orders of magnitude slower than memory. And so all of the operations that we're doing, the algorithms that we're choosing to implement, these are all with an eye toward please as few disk IOs as possible. They're the bottleneck for us. And this comes out of a world where in the 1970s, when kind of the System R, the first relational databases were being created, we had a single CPU in computer systems. Memory was severely limited. RAM was really expensive. You couldn't have much of it in a system. So the database had to be stored on disk, and disk was very slow. So all these design decisions, which still influence many databases that are heavily used today, that's kind of the world this is coming from. But it's becoming the case that DRAM, the kind of technology the storage technology that makes up main memory, the sizes have gotten way up, the cost has gone way down, and so it's now possible that you would have gigabytes or even possibly low numbers of terabytes of DRAM on a system. And sure, there are many databases that still aren't going to fit in that, but there are many that are. And so all these design decisions that were made with our data is always going to be on disk, they don't really apply, or many of them don't apply when we think about in memory. And so there are kind of a number of other potential bottlenecks that arise when we're not, when the disk is not the obvious and overwhelming bottleneck. So we start thinking about what is the cost of locking or latching, not just waiting for locking and latches, which we did think about for our disk-based system, but just the actual, like, the time it takes to acquire and release locks and latches may start to seriously matter when we're not doing disk I/O. We may have to think a lot more about the cache performance of our code, meaning that caches providing faster access to small amounts of frequently used memory in computer systems. Our database may need to be a lot more concerned with implementing cache-aware, cache-efficient code. We may need to beware of following chains of pointers. That if we have like a a linked list or some sort of structures that involve kind of following a bunch of pointers with each lookup. When we're doing disk I/O, like a bunch of memory accesses still look super fast. When we're not, following these chains of pointers may turn out to be a bottleneck. Predicate evaluation, just the sort of computing predicates on a whole bunch of tuples, copying data around may becomes an issue, as well as networking. If an application sending transactions or queries to the database and getting them back, that may actually be the slowest part of this process when we're talking about an in-memory database. So there are a whole bunch of new things that we might need to optimize when we're dealing with in-memory database to get the best performance. Another interesting point. We no longer necessarily need to store our data nearby, like next to each other, not necessarily contiguous in memory, because we had to do that on disk because sequential reads on the disk were much faster than random ones. When we're talking about memory, it's random access memory. We're not really concerned with needing to do sequential reads all the time. And so just the priority that everything be read and written sequentially, that kind of goes down in priority. Our iterator model of query processing also is going to be too slow when we're talking about an in-memory database. Just the fact that we have to do a separate function call, a separate call to next every time we want a tuple, the overhead of those function calls starts to matter when we're dealing with an in-memory database. So much more common to see the vectorized or the materialization models of query processing for our in-memory databases. And finally, it's not the case that we have no use for disk at all, or we never interact with the disk for an in-memory database. It's still the case that DRAM, for example, doesn't maintain the value stored in it when it loses electricity. And so just because our database is in memory doesn't mean that we don't need it to be persistent. That it's okay if it just disappears, if the system goes down. But this means that we don't need to write out everything to disk. We don't need to put all the data on disk. If we have logs and checkpoints on the disk, that will be enough to make our database persistent, and so it sort of changes how we're going to achieve persistent data. And this may be changing, or already is changing, kind of with the rise of new storage technology. There are several kind of developing storage technologies that are kind of memory that can remember or keep its values even when it doesn't have electricity. And this could kind of fundamentally change the way that databases are built if these sort of technologies become widespread and aren't just sort of cutting edge and experimental. So I hope that gave you a bit of a sense of kind of some of these big ideas and areas outside of what our focus was on this term. One other thing that I have discovered is ever since the Void got into my computer, I have been trying to figure out how to deal with that, reading documentation on the course, and something that I discovered is that there's actually a course configuration file. I mean, who knew that there was just a course configuration file that you could edit that set everything up for the course, and naturally, there's just a void flag, and it was true this whole time. And all I needed to do to deal with the void is set that flag to false. So, mission accomplished. Hit it.